All right, welcome to Physics 2425, Lecture 13B, Rotational Dynamics. So we've already looked at rotational kinematics and the fact that our angular speed can change over time. And we've looked at torque, which causes changes in rotation. And we've looked at equilibrium situations. Now we're going to look at dynamic situations. So we're going to link torque to angular acceleration. Now, Newton's second law for rotation comes from Newton's second law in linear terms. There's a direct correlation. So our Newton's second law in linear terms tells us that our linear acceleration is our net force over mass. Our Newton's second law for rotation says that our angular acceleration is net torque over inertia. What this tells us is that when a rigid object is subjected to a net torque, it undergoes an angular acceleration. But what determines that angular acceleration, the amount of the acceleration, is inertia. So mass was the equivalent of linear inertia. The more mass an object has, the more resistance to changes in its motion. So I'd have to apply a bigger force to get the same acceleration if I have a larger mass. Well, what's the rotational equivalent of that? Well, the rotational equivalent is rotational inertia, which we use a capital letter I. So it's sometimes called rotational inertia or moment of inertia. So it provides resistance to rotation. It's related to mass, but it's also related to where the mass is located. So we need to dig in on what this moment of inertia, the rotational inertia, actually means before we can go on and learn to solve problems with rotational dynamics. So rotational inertia, if you have a single point mass, for example, this point mass M right here, that is located at some distance r from an axis of rotation. So this axis of rotation here is perpendicular, in this case, to that r. Then the rotation inertia is going to be mr squared. Okay, so that's for a single point mass. Now, if you look at the units here, mass is in kilograms, radius SI is meters squared. So we don't have a fancy unit like a Newton or something for this. So it's just kilogram meter squared. The rotational inertia is dependent on the axis of rotation. So if you look at a different axis, you will get a different rotational inertia. Your moment of inertia is larger when the mass is located further from the axis of rotation. So the bigger and bigger r gets, the more and more rotational inertia an object is going to have. Now, if you have a collection of point masses, say we have an axis of rotation here that's at the center of this system, then you basically just add them all up. So I is going to be the sum of all the little mi ri squared. So you take one of these, and then the next one, and then the one after that, and the one after that. Okay, and basically you put in their masses and their radii. So for one, you would have R1 is going to be B, and then R2 is A, and then R3 is B, and R4 is A. Okay, so you have to measure those always from the axis of rotation. And here it's nice the values they gave us for length are the same thing as the axis of rotation. But remember, you can change your axis of rotation. For example, instead of using point O here as the axis of rotation, what if my axis of rotation was where that mass was located? Well, then this mass would have an R equal to 0. So it wouldn't have any rotational inertia. It's not providing any resistance. And then this mass would have an R that is based on the triangle right there. And then this one over here, its R would be A plus, or would be B plus B, so 2B. And this one would have an R there. So you change the axis of rotation, you change your R values, okay? So the distance to the axis of rotation. So let's look at an example of how to do this. So let's consider we have these 4 point masses. They're all identical, so we can just assume that they all have an M that is equal to 0.200 kilograms. Okay. The rods themselves are thin and they don't give us any information about them, so we can assume that the rods have no mass. So they're not going to have any rotational inertia. We're going to assume that our axis of rotation goes here between A and B. I'm going to assume that this one is 0.1, 2, 3, and 4. So when you're doing this, our rotational inertia is through the line. So when we do our distances are the short distance directly to the line. So that's R1, that's R2, that's R3, and that's R4. So because I think we're going to assume that this thing is a square. Didn't specifically say that, but we're going to assume it's a square. So in this case, all of those R's are half the length. So the whole length is 0.4, so half the length is 0.2. So R is going to be 0.200 meters. So the rotational inertia is going to be m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. That was a cube, sorry, squared. Right there. So they're all identical though. They're all the exact same distance away with the exact same mass. So I can just say that I is going to be 4 times m1 r1 squared because they're all identical. Now if they had different masses, you wouldn't, and different distances, you wouldn't be able to simplify it. But you're going to get 4 times 0.200 kilograms times 0.200 meters squared. That gives us a rotational inertia equal to 0.032. 368, so I should add another 0 on there, kilogram meter squared. Okay, and that's about that axis going through along the line AB. If you were to change the axis, you would get a different value. So you just have to kind of be careful about what they're asking for. All right, but what if you don't have a point mass? We did this with center of mass. It's very, very similar. So picture that we have this long thin rod. You treat every, let's get a better color. You kind of break this up into infinitesimally small slices, each with a mass dm, a thickness of dx, and they'll be at positions of x. I'll have like x equals 0, and I'll have like x equals L. And the idea is that you add those all up because each one of those infinitesimally small bits is going to have some amount of rotational inertia. If you take the limit as that mass gets smaller and smaller and smaller, then your delta mi becomes a dm. And you end up with your rotational inertia being the integral of r squared dm. If you don't have a line, you might need to do an area or a volume. So in general, the most general kind of definition of here is I is the integral of rho r squared dv. And that's because we can define dm as rho dv. Because remember, rho is equal to dm over dv. We could have sigma equal to dm over dA. And we can have lambda equal to dm over dl. So it doesn't really matter which way you do that, but if you go online and look at videos, you might see some resources always use that definition. That's not generally how I work. I kind of work based off of the fact that I is equal to the integral of r squared dm, and then I use these to substitute in for dm. But this one is actually the most general definition. It will kind of work for everything. So, for example, I would use the dm equals lambda dx for like a long thin line. For a sheet, I would use the dm is equal to sigma dA, and for a volume. So this is actually hollow cylinders. So picture these hollow cylinders here. They are empty in the middle, okay, but they have a thickness. Their thickness is equal to dr for the thickness. And then they each have an individual radius. So we're going to practice this with a long, thin line. So we're going to go through this whole process of how you would solve it. So what we do, if we want to find this long, thin rod, so we're going to assume that it has a mass of m and a length of L. I didn't say that, but I'll add the length of L in as a known value because it's on here on our diagram. So we're going to rotate it about an axis through its center of mass. So we're going to assume that this guy is uniform, in which case its center of mass is going to be the exact center of the rod. So I'm going to set up a coordinate system in which x equals 0 is my axis of rotation. And then that makes the left end of the rod a position of negative L over 2, and it makes the right end of the rod a position of positive L over 2. You pick an infinitesimally small section. That section is going to have a mass of dm and a thickness of dx, and it's going to be at a position of x. So basically, its r value is x. So what we're going to do is we're going to assume that we have I is going to be the integral of r squared dm. But I'm going to use the fact that my linear mass density is dm over dx. So dm is going to be lambda dx. I'm also going to assume that lambda is equal to m over L because I'm going to assume that it's uniform. If not, remember they can give you a function, lambda of x, to substitute in instead. Or maybe they'll just say lambda is a variable that you know, okay, at some density lambda that you could just keep in there. So I'm going to sub that in right up here. So I'm going to get dm is equal to m over L times dx. And I'm going to do that change of variables because I want to integrate in x from the left end of the rod to the right end of the rod. So I need to get my differential there in terms of x. So I is going to be the integral. Now I'm defining r as an x value. So I'm going to do that x squared. And then dm is m over L dx. And I'm going to integrate from the left side, negative L over 2, to the right side, positive L over 2. So I is going to be, I'm going to pull the m out over L out in front because it's constant. And then the integral of x squared dx is going to be 1/3 x cubed, evaluated from negative L over 2 to positive L over 2. So you need to sub in your limits. So I'm going to have m over 3L. And then I'm going to get the difference between L over 2 cubed minus a negative L over 2 cubed. Be careful with your signs on this. So this is going to give us m over 3L times L cubed over 8. And then negative L over 2 cubed is still negative, so that's going to be a positive L cubed over 8. So that's going to give me m over 3L times L cubed over 8 twice. That's going to be 2L cubed over 8. So that reduces. So you're going to end up with 1 over 12 ml, and there's an L on the bottom and an L on top, L squared. So the rotational inertia of this rod is 1/12 ml squared when rotated about the center. Now, your rotational inertia is always going to be smallest when you rotate an axis about its center. And that's because you're going to keep your endpoints as close to the middle as possible, making your R values smaller. If I was to say instead, rotate this rod about one end, then my X value would be on the far side, and I would set this side equal to x equals 0, this side equals to x equals L. And in this case, I would integrate from x equals 0 to x equals L, and I will get a different function. but with a very similar kind of solution to it. So very similar problems. Now, a lot of these formulas are known formulas that you can just look up. So for example, when you rotate a long thin rod about its center of mass, it's 1/12 ml squared. Hey, we did that right. Isn't that amazing? If you rotate that same rod about one end, you get 1/3 ml squared. And 1/3 is a larger fraction than 1/12, telling us that a rotational inertia of the rod is larger when rotated about an end. And if you kind of think about it, if you want to spin like a baton quickly, like a twirler, they're going to spin that baton about the center. And it'll spin slower if they try and do the same thing about one end. If you have a hoop or a thin cylindrical shell, it actually has the same formula as that of a point mass. And that's because if I was to look at this from the top, so picture that I have my hoop and I'm going down here, whether it's thin or thick, it doesn't really matter what the length of this is. It doesn't come into play, because if this is my axis of rotation at the center, every little infinitesimally small piece is a distance of r away from the axis of rotation. So you're basically adding up all those infinitesimally small point masses so that the whole mass m is located a radius of r away. So it has the same formula as the point mass. Now your solid cylinder is 1/2 mr squared, which is a smaller fraction. And that's because some of the mass is actually located really, really close to the axis of rotation through the center, making a smaller rotational inertia than that hoop. And actually part of the reason we use hoops for bicycle wheels is because providing that rotational inertia makes it a lot easier to keep the bicycle going and rotating. It makes it more stable. If you were using solid wheels, like solid disc for your wheels, it would be a lot harder to keep the bicycle stable, because you'd have lower rotational inertia, so less tendency to keep on rotating. The spheres, same kind of idea. So your thin spherical shell has all of your mass located at a radius of r, but it rotates through a center, and so some of the mass is located in contact. So you're going to get 2/3 mr squared. The solid sphere is 2/5 mr squared. So you're going to have much more mass located towards the center. 2/5 is a smaller fraction than 2/3. It's a good idea to memorize these formulas. There are times where I will give them to you if I'm not testing you over the concepts and I'm just having you use them at a problem. I might give you the formulas because I don't want you to get the problem wrong just because you memorize something wrong. But I might ask you conceptual questions about the rotational inertia of these guys. And you'll need to understand why their formulas are the way they are. Not just, oh, I memorized this one's 2/3 and 2/5, and 2/5 is a smaller fraction, so therefore it's a smaller rotational inertia. Why does the solid sphere have the smaller fraction? Well, it's because more mass is located closer to the axis of rotation than for the hollow sphere. So you have to be able to kind of rationalize based on the distribution of mass. And that's the most important thing for rotational inertia, is it is based on the distribution of mass. So when you're answering conceptual questions, you want to refer to the distribution of mass relative to the axis of rotation. There is a theorem called the parallel axis theorem, which basically says if you know the rotational inertia about the center of mass, so for example, about the rod right here, about its center of mass, and you wanted to find it about any other point, you can use this formula. So picture that this wibbly wobbly thing. We know the rotational inertia about the center of mass, and we know where that center of mass is located. If I knew the distance d here and the mass of the whole thing, I could find the rotational inertia, say about 0.0 right here. And I can figure out what is that rotational inertia by taking whatever the rotational inertia is for the center of the mass plus mass times the distance between those 2 points squared. It's actually a pretty simple formula. So we can prove this because we know the formula about this point here. We know that this is about the end is 1/3 ml squared. And we know about the center is 1/12 ml squared. So we can prove that this formula works without having to go through and setting up our calculus. So I could do that. I could set up x equals 0, x equals L. I could take this point, which is at a distance of x, and I can set up that equation and go through the process that we did before using calculus. Or I can use the parallel axis theorem. So I'm going to call this point P right here, this axis right here. So the rotational inertia about point P is the rotational inertia about the center of mass plus md squared. Well, d is going to be this distance between the center of mass and point P. In this case, d is equal to L over 2. So I about point P is the I of the center of mass, which is 1/12 ml squared, plus m, d is L over 2. So I get 1/12 ml squared plus 1/4 ml squared. And if I get a common denominator, that's going to be 3/12 ml squared. So I about point P is 1/12 plus 3/12, which is 4/12 ml squared, which is 1/3 ml squared. So isn't that nice? So as long as I have a uniform rod, and this only works if uniform, then I can use my parallel axis theorem to find the rotational inertia about any point along this rod. Or let's say I had my formula for the hoop. I, the center mass of the hoop, is just mr squared. If I wanted to instead rotate it about a point on the end so that that center makes a loop around, so that this thing makes circles around that point, then I could do the same thing. D would be the distance, would basically just be the radius r. So I can use this for any of those formulas, assuming that the object is uniform. If it doesn't have a uniform density, it doesn't work that well. Once you know what the rotational inertia is, using calculus, using the formulas, then you can kind of go through and solve any other problem using Newton's second law for rotation. So the general process for solving dynamics problems using net torque is equal to I alpha is going to look very similar to solving net force equations. So you're going to start with an extended body diagram. You're going to label all of your forces. Okay, you have to choose your axis of rotation. They will usually give you the axis of rotation in equilibrium. It is truly arbitrary, and it can be anywhere. But for our rotational dynamics problems, they will probably tell you where the axis is. Okay, you draw your position vectors for those lever arms. Okay, you determine which forces create torque. You write net force, net torque equations. You solve for your system of unknown and so forth. Okay, sometimes you don't need the net force equations. Sometimes you just need net torque equations. But there's some cases where you may need both, especially when there's both linear motion and rotational motion going on, such as if you have a pulley that is rotating. At the same time, you have a block that is moving linearly. You might need both. So let's look at our Atwood machine. We're going to start with that most basic Atwood machine. So in this case, we're going to assume that our pulley does not have a negligible mass or friction. So we're going to assume that our pulley is going to rotate with our mass. So that we're going to have a linear acceleration for mass 1 down, because it's the more mass of 1, and a linear acceleration of m2 up. Those are going to be the exact same magnitudes because they're connected by the rope. And then this is going to cause an angular acceleration in our pulley. So we're going to assume that our pulley is a uniform solid cylinder of mass m and radius r. And we want to find the acceleration a of the blocks. So just as a reminder, when we solved this problem before, ignoring the mass of the pulley, we basically said that mass 1 is going to have a gravitational force down and a tension force up. Mass 2 is going to have a smaller gravitational force down, but the same tension up. And we said that the net force on block 1 in the y direction was going to be Fg1 minus Ft, which is equal to M1A. We said that in the y direction for block 2, that was going to be Ft minus Fg2, which was equal to M2A. we define the positive direction is down for M1 and the positive direction is up for M2 to keep our signs from getting wonky. We said that that the tensions were the exact same. So a lot of that is the same here. But the problem is, according to Newton's second law for rotation, net torque is equal to I times alpha. So in order for the pulley to have an angular acceleration, there has to be a net torque. So what forces are acting on the pulley and what causes torque? Well, there's going to be some sort of gravitational force on the pulley, and there's probably an axle here for the pulley that the pulley is resting on so it doesn't fall, creating a normal force. And then basically we assume that those tension forces are pulling down on the sides of the pulley. Technically, it's a friction force that's being translated through the tension, but it's sufficient to assume that that tension force is equivalent to the friction force, so we're okay. But basically, those tensions are pulling down on the sides of the pulley. So the gravitational force and the normal force are acting at the axis of rotation of the pulley, which means they are not creating torque. So the only torques can come from those tensions because those tensions are acting at a distance of r. And we assume that the string is acting when the tension is perpendicular to the radius so that we don't need to worry about any angles. So here's the conundrum. If each of those strings is creating an equal torque, they are creating torques in opposite directions. If they have the same radius and they have the same tension, they will have equal torques in opposite directions, and there would be no net torque. And it would be impossible for that pulley to have an angular acceleration, which means the system would not move. So the biggest issue that we have here is that the assumption we made that the tensions were identical in both strings is completely wrong and not true when we have to include the pulley. So I'm going to call the tension 1 the tension in the left rope, and tension 2 the tension in the right rope. And tension 1 has to be larger than tension 2 in order to have that angular acceleration, which means the torque due to tension 1 has to be larger than the torque due to tension 2. So we are going to create an angular acceleration. So starting this problem again, we have that our net force in the y direction for block 1 is going to be Fg1 minus Ft1, and that's going to equal M1A. We have a net force in the y direction for block 2, which is going to be Ft2 minus Fg2, and that's going to equal M2A. And we have a net torque equation, which is going to equal the torque due to Ft1 minus the torque due to Ft2, and that is going to equal I times alpha. And that's for the pulley. So we have the net force on block 1, the net force on block 2, and the torque on the pulley. So working through these, we're going to start subbing in. So for the Fg1, that's going to be M1G minus Ft1 is equal to M1A. For the second block, we're going to have Ft2 minus M2G is equal to M2A. For the torques, the torque due to tension 1 is going to be Ft1 times R. Torque due to Ft2 is going to be Ft2 times R because we're assuming those are at 90-degree angles, and that's going to equal I times alpha. So our goal is to find the linear acceleration of the blocks. So without the pulley, we only needed our 2 net force equations. But the problem here is we now have 3 unknowns. Our 3 unknowns are we do not know Ft1, we do not know Ft2, we do not know the linear acceleration in those 2 equations. So that's 3 unknowns in 2 equations. So we need at least a third equation. When we look at the third equation, we don't know Ft2, Ft1, We have I, we know it's a uniform solid cylinder, so we can assume that our I is 1/2 mr squared. This would be the type of problem where I would give you the formula for the rotational inertia, because that is the least problem that I need you to have, is guessing the right one in a problem this complicated. And now we've also introduced a new unknown value, alpha. So if I look at this, I actually have 4 unknowns, but only 3 equations. So it seems like I'm stuck. But we need to make one more assumption. When we look at the pulley, what we're going to assume is that the string has a linear acceleration of a, and that there is enough friction between the string and the pulley so that the point of the string that is touching the pulley, that those move together. So that those are going to travel together at the same rate the whole time. Starting here at the point where the string first comes into contact with the pulley, and then those are going to continue together. So what we're going to assume is that the linear acceleration of the string is equal to the linear acceleration of the rim of the pulley. Now, the reason I want to make that assumption is because the angular acceleration, alpha, is related to the linear acceleration of the rim of the pulley by the radius r. Remember, we said that the tangential acceleration is equal to r times alpha. And in this case, our tangential acceleration is the linear acceleration of the rim of the pulley. So what we can assume is that the linear acceleration, a, is equal to r times alpha. And what that allows me to do is it allows me to replace alpha with a over r. So I'm going to make that insertion right there. So you get ft1 times r minus ft2 times r is equal to, I'm going to use I as 1/2 mr squared, and alpha is a over r. So that's something you're going to do every time. You could do this exact same process solving for alpha. If you did that, you would replace all of the a's with r alpha instead and get everything in terms of alpha. So if I look over here at my torque equation, I can cancel an r here on the bottom with one of those r's. I can also, when I do that, I now have an r in every term, so I can cancel r. So actually, they don't have to tell me the radius of the pulley. This equation simplifies down into ft1 minus ft2 is equal to 1/2 m times a, where that m is the big M, it's the mass of the pulley. Now, if this was a different type of pulley, like the pulley was made out of a hoop, this coefficient right here is different depending on the type of my pulley, because that comes from my rotational inertia, but everything else in this problem is going to be the same. So now what I'm going to do is I need to find a way to get rid of ft1 and ft2, because I'm looking for a. I've gotten rid of alpha. Now I need to get rid of ft1 and ft2. So I'm going to do that over here. I'm going to solve this equation for ft1 and this equation for ft2. So ft1 is going to be m1g minus m1a. I'm going to add ft1 to the right and subtract m1a to the other side. And then ft2 is going to be m2a plus m2g. I'm going to take those and sub them in to my torque equation. The order that you do the subs in doesn't matter. This is just always what I do. I always solve the net force equations for tensions and plug them into my torques, but that's not the only way to do this. So I'm going to take that ft1 right here. It's going to be m1g minus m1a. And then subtract ft2, which is m2a plus m2g. And that is equal to 1/2 big M for the pulley times a. So I get M1G minus M1A minus M2A minus M2G is equal to 1/2 M times A. And then what I'm going to do is I'm going to get all the A terms on one side and the G terms on the other. So that's going to give me M1G minus M2G is equal to M1A plus M2A plus 1/2 MA. I can then group all the A terms together and the G terms together. I'm going to get M1 minus M2 times G is equal to M1 plus M2 plus 1/2 of M times A. Come over here, solve for A. A is going to be M1 minus M2 times G over M1 plus M2 plus 1/2 of M. And that is my acceleration. So a couple things that we notice. If there was no pulley, if we assume the pulley was massless and frictionless like we did before, the only thing that would be different is this term. That's the only thing that is being contributed by the pulley. But you can see that that term is in the denominator, so it's contributing to the overall inertia, because the top of this is the net force, and the bottom of this is inertia, because acceleration is net force over inertia. So the rotational inertia is adding into the denominator. So our acceleration, including the pulley, is going to be smaller than if the pulley had been massless and frictionless. Now, since there's no such thing as a massless and frictionless pulley, when we're doing experiments with Atwood machines, we usually get accelerations that are smaller than expected, not just because of friction, but because the net force has to move not just the two hanging blocks, but also the pulley. So very, very common type of problem. You can get lots of rotational dynamics problems. I focused on the Atwood machine because it's the most complicated out of them. So our next topic is rotational kinetic energy. So rotational kinetic energy you can kind of derive from linear kinetic energy, because if you treat each individual particle as having a mass and a velocity, a linear velocity, that tangential velocity, then you can have each particle has some sort of kinetic energy. And depending on which particle you're looking at, you're going to have a different radius for each. So particles that are further out are going to have a different radius. So when you start looking at the linear versus the angular, you can use VI here to convert that tangential velocity into an angular velocity. So if we make that substitution in here, what you get is that the kinetic energy of one of those individual points is going to be 1/2 mi omega squared ri squared. So if you add up all of those individual point masses and you rearrange and get that sum of all the little mi ri's, we can then replace that I with the total inertia of the object, and our rotational kinetic energy is 1/2 I omega squared. Now, if an object is just rotating, it has rotational kinetic energy. If an object is just translating, it has only translational kinetic energy. But you could have an object that is rolling, and it has both an angular speed and a linear speed. So it can have both translational and rotational kinetic energy. So these are two completely different quantities. If you have pure rotation, you just have rotational kinetic energy. But if you're rolling, you will have a combination of both. So when we start looking at rolling, it's a combination of translation and rotation. So translation says if the object was just sliding, moving horizontally and not rolling, then every point on the wheel is going to have the same velocity as the center of mass. If the object was rotating with some sort of omega, then every point on the rim is going to have a tangential velocity. That tangential velocity is equal to r times omega. So pure rotation says that each point on the rim is going to have a linear speed. That linear speed is equal to r times omega. The center is not actually rotating, it's just moving at a speed of VCN. So if you add all those vectors together, the center has just the velocity of the center mass because it's not rotating. This point up here at the top has the velocity of the center mass and the velocity of the center mass. You add those together and you get 2 times the velocity of the center of mass. So the point at the top is actually moving twice as fast as the center. The point on the bottom has the velocity of the center of mass going to the right from the translation, but that point's actually moving to the left in rotation with the same speed that it would be translating at, so those actually cancel out. So the point at the bottom is actually instantaneously stationary. And this is really important because there's actually no slipping. If we were slipping, we would have kinetic friction and we would lose energy. But we assume that when we roll, that there is no energy loss to friction. There is friction because you can't actually roll without friction. Picture if you're trying to drive your car on ice and you're stopped and you try to gun it and your tire's just going to spin in place because there's not enough friction for your tires to move forward. So in order to roll, we do need to actually have friction. But because we assume no slipping, because the point at the bottom is instantaneously at rest, there is no frictional losses. Now, at these points on the side, like point 2 has a horizontal VCM from the translation and a vertical VCM from the rotation. So its net velocity is at an angle, and same as at the other point. Okay, so they're actually going to have, every point's going to have a different magnitude of the speed and a different direction. When we look at rolling on an incline, which is going to be our most common case, what happens is you have 3 general forces. So your gravitational force acts at the center of mass. The normal force, its point of contact is the ground, and it still operates perpendicular to the surface. And then there is going to be a friction force. So the friction force here is pointed up the ramp. What's kind of cool is the friction always points up the ramp, whether or not it's moving up or down. So let's assume that I start this guy at rest. So I release this thing from rest. So at this instant, it has no linear speed and it has no angular speed. Over time, it's going to gain a linear velocity and it's going to start rolling with an angular velocity. So in order to increase in angular speed, there must be a net torque. So you're going to have an angular acceleration. Now, where does this angular acceleration have to point? Well, if I'm going to speed up, my angular acceleration has to be in the same direction as the angular velocity. I need a force to cause this angular acceleration. Well, gravity is not creating any torque because it's acting at the axis of rotation. The axis of rotation of a rolling object is its center. So gravity is acting at the center, so the torque due to gravity is 0 because you need to have a lever arm distance. Now, normal force also is not creating the torque, and that's because the normal force is parallel to its lever arm. So the lever arms drawn from the axis of rotation to the point at which it's applied, those are parallel, actually anti-parallel, but still the cross product comes out as 0. So that means it's the friction force that is creating the torque for rolling. And if I need my angular acceleration to be related to that clockwise motion, then I need that friction force to cause that, in which case it has to point up. Because if my friction pointed down, that would be creating a rotation in the wrong direction. So I need my friction force to point up the ramp. Now, if I look at it this from the opposite direction, so let's assume that it's already rolling when it gets on the ramp. So it's moving with the linear speed of VCM, and it has an angular speed because it's rolling up that ramp. Eventually, it's going to stop. And so this is going to have to come to a stop up at the top. And it has to be slowing down. It's going to slow down. Well, if it's going to slow down, I need my angular acceleration to be in the opposite direction. Well, once again, my gravitational force isn't creating torque. My normal force isn't creating torque. It's only that friction that can create a torque because it has a lever arm value that is non-zero and it is perpendicular to the lever arm. So the torque due to friction has to be there. Now, notice that my angular acceleration is in the same direction it was in the other way. It needs to go this way. So that means my friction still has to be up the ramp. Because if my friction was down the ramp, that would cause a rotation in the wrong direction. So this friction is always up the ramp. Let's say we wanted to find the linear acceleration of this thing as it rolls on the ramp. Now, if you recall, when we looked at ramps before, the linear acceleration on a ramp was always straight down the ramp. And that linear acceleration was equal to g sine theta, assuming that there was no friction, okay, if this was a frictionless ramp. So what we're going to do is we're going to figure out, well, what is that acceleration, that linear acceleration now? So I know that in terms of my forces, when I was working ramp problems, I rotated my axes so that I had both an x and a y component of gravity. So I'd have an FG x here, and I had an FG y. And I'm going to assume the positive x direction is down the ramp, positive y direction is up the ramp. So in terms of my net forces, my net force in the x direction is going to be FGX minus that static friction force, and that has to equal m times a. In the y direction, I'm going to have Fn minus Fgy, and that has to equal 0. So I know that my friction force, and notice that this is a static friction force, because we said that rolling does not involve slipping. So this rolling friction is a static friction force because there is no sliding going on. There's no kinetic friction. So I want to find, assuming that it's rolling without slipping, when I do that, I actually don't know the mu Fn. Okay, they're not giving me a value for mu. So because I'm not at the point where I'm slipping, my static friction force does not equal mu s Fn. So I can't use that equation to solve this problem. So Fs cannot be substituted with mu Fn. Now, Fgx is going to be mg sine theta like normal, because that's our angle theta. Fgx is the opposite side. So minus Fs is equal to m times a. So Fs cannot be found using this equation. So I need to find another way to find my friction force. Well, we've already mentioned that that friction force is actually causing the torque. So I know that the net torque is equal to the torque due to friction, and that's equal to I times alpha. Okay, we're going to just assume that this can be any object that rolls. So instead of using a cylinder, which is 1/2 mr squared, or using a sphere, which is 2/3 or 2/5 mr squared, I'm just going to use 1/x. Okay, and x represents whatever portion of the fraction that's given. This is just going to be really general, so you can kind of see how this would change for different objects. Well, the torque due to friction is going to be my static friction force times r, because those are at 90 degrees, so r and my static friction force. And then I'm going to use 1/x mr squared times alpha. Now I have the same problem that I did for the Atwood machine, and that is I've just introduced a new variable. But we do know that if we're rolling, that there is a link between the angular acceleration and the linear acceleration of the center of mass, and that is a is equal to r times alpha. So that means that I can replace alpha with a over r. So my static friction times r is going to be 1/x mr squared times a over r. So now I can go through and I can cancel one of the r's here, and I can cancel my other r. So once again, I actually don't need to know the radius of this wheel. It's independent of radius. So all wheels with the same shape, regardless of what their radius are, will have the same acceleration. We're going to Fs is equal to 1/x m times a. So both of these equations have an unknown Fs in them and an unknown A. So what I'm going to do is I'm going to take this equation and plug it in for SF over here. Fs, sorry, mg sine theta minus 1 over x ma is going to be m times A. I'm going to get the A terms on the same side, so I get mg sine theta is equal to 1 over x ma plus ma. Notice actually that the mass cancels out as well. So the mass doesn't matter, the radius doesn't matter. The only thing that matters is the angle of the ramp and whatever the shape is. So I get g sine theta is equal to 1 over x plus 1 times A. If I wanted to get a common denominator here, I could. I don't think it particularly matters, but A is going to be g sine theta over 1 plus 1 over x. What this tells me is it tells me that I'm taking a very similar equation, g sine theta, and then the only thing I'm doing is I'm adding in this term into the denominator that is based on the general shape, whether it's a solid sphere, a hollow sphere, and so forth. This whole coefficient right here, that is the big determination. So the larger the fraction, the smaller the acceleration. And the larger the fraction, it means large rotational inertia. So we could summarize this by saying that the larger the rotational inertia, the smaller the linear acceleration. So the more resistance you have to rotating, the smaller and smaller the acceleration goes. Now, we can also analyze rolling on an incline by taking a look at energy. If we're not looking specifically for acceleration, but wanted to instead find how fast is a ball rolling at the bottom, or which ball is going to make it to the bottom fast, the solid sphere or the hollow sphere, we can use energy. So what we would assume here is that the ground is going to be y equals 0, and we're going to start at some height h. And I'm going to assume that my potential energy is 0 at the bottom. And in this case, we're going to start off with no kinetic energy at the top, because we're going to start from rest. When we take a look at energy here, we have the kinetic energy at the start plus the potential energy at the start is equal to the kinetic energy at the bottom plus potential energy at the bottom. This looks exactly like we would have done before we learned about rotation. The only problem here is that as this thing starts to move, it has both a linear speed and an angular speed. So our kinetic energy is a combination of translational and rotational. So we have k trans at the start plus k rot at the start plus our gravitational potential energy. And that's going to equal k trans at the bottom plus k rot at the bottom plus our gravitational potential energy at the bottom. Now, we're going to assume that this thing starts at rest. And if it's at rest, it's rest both linearly and rotationally. And we're going to assume that our energy at the bottom is 0, so U2 is going to be 0. So I have U1 is going to be mgh. K trans 1 is 1/2 mv squared. K rot 1, K trans 2, speed at the bottom. K rot 2 is going to be 1/2 I omega squared. Actually, don't really need that subscript for the 2 here because there's only one velocity, the velocity at the bottom. So what I have here is I have an equation that involves my starting height, which I know, but involves both my linear speed and my angular speed. But I want to know what is the linear speed of the ball. So I need to get rid of that angular speed. So once again, the linear speed of the center of mass is equal to r times omega. So I can substitute in omega is equal to v over r, where that velocity is the linear velocity of the center of mass. And that's the same velocity that we're using here in the translational, because that is the linear motions based on the center of mass. So I get mgh is equal to 1/2 mv squared plus 1/2 my rotational inertia. Let's see, it says a ball. So a ball, let's just assume that it is going to have the 2/3 mr squared, which is the fraction for the hollow sphere. So this is going to be like a hollow sphere, not like a bowling ball. So we're using the 2/3 mr squared. So I'm going to use 2/3 mr squared here. And omega, if I do omega squared, it's going to be v squared over r squared. So using that capital R there. So I could sub in v squared over r squared. So one thing you're going to notice that once again, r squared cancels out. So the radius doesn't matter, just like it didn't matter for acceleration. The only thing that's really going to matter here is the height and whatever that fraction was for our rotational inertia. So I get mgh is equal to 1/2 mv squared. The halves cancels with the 2, so I get 1/3 mv squared. So notice that mass cancels out as well. So the mass doesn't matter. I can combine those fractions. So with a common denominator, I can get 3/6 and 2/6. So we get GH is equal to 5/6 v squared. So if I solve for the speed, our speed is going to be the square root of 6 over 5 times GH. Now, if this ball had been sliding down the ramp on a frictionless ramp, if it was a frictionless ramp, first of all, it cannot roll. If it is frictionless, it cannot roll. So if they tell you it's a frictionless ramp, it's not rolling. Okay, it would have been the square root of 2GH. 6/5 is less than 1. So we can see that by rolling, it's going to have more resistance to changes its motion. So it's actually going to be going slower at the bottom of the ramp than if it had slid down the frictionless ramp. Our last major rotation topic is angular momentum. So our angular momentum is given the variable capital L. It is a vector. It has units of kilogram meter squared per second. So thinking back to linear momentum was mass times linear speed. So you basically had an inertia term and a motion term. So our angular momentum is very similar. So except for if we're dealing with rotation, it's not linear inertia, it's not mass, it's rotational inertia. We're talking about our angular velocity. So angular momentum for an extended object is defined as I times omega, rotational inertia times omega. Rotational inertia is kilogram meter squared. Our angular velocity is radians per second. The radians is a placeholder, so it cancels out. Now, remember that our direction of the angular velocity is perpendicular to the plane of the rotation, so that if you are rotating counterclockwise, that is a positive angular velocity, but actually points straight up out of the page. Our angular momentum is in the same direction as our angular velocity because rotational inertia is scalar. So you can use your right-hand rule to figure that out. Curl your fingers in the direction of rotation, where your thumb points is where both the angular velocity and the angular momentum point. Just like our linear momentum is always in the same direction as our linear velocity. The angular momentum is the same direction as omega. We assume angular momentum is positive when we have counterclockwise rotation and negative when we have clockwise rotation. That is the course of convention, and you can pick your direction to be whatever you choose if it's not defined for you in the problem. Now, if we have a point mass, we can look at this in a slightly different method. So objects actually do not have to be rotating to have angular momentum. This is one of the most misunderstood concepts and actually is the whole basis for quantum spin in chemistry. If you've done that, for that course. The idea that your electrons can spin two different directions is based on angular momentum, but our electrons actually aren't sitting there spinning in place. They're actually moving in straight lines, but they still have angular momentum. So picture here that you have a point mass that is some position r from the axis of rotation that is moving in a straight line, in that direction with momentum p. Okay, and there is some angle phi between the position vector and the momentum vector. We know by definition that our angular momentum is I times omega. So if you sub in I for a point mass, you get mr squared. But omega, by definition, is our tangential velocity times r. I'm using perpendicular to be consistent kind of with cross products, but it is a tangential velocity. So if we assume that omegas are v perpendicular over r, then when you substitute that in for omega, you get that our angular momentum is m v perpendicular times r. But m times v perpendicular is the same thing as the perpendicular component of the linear momentum relative to r. So we can define angular momentum for a point mass as being based off of a cross product. So any rule that you do for cross product will work. So you could use matrices in 3 dimensions, or you can use r perpendicular times p, p perpendicular times r. Or you could substitute in that p is m times v, m's a scalar, pull that out, and you can use this version as well. So you can do that for a point mass. So it's really important to realize that these point masses are not rotating. They are moving in straight lines, and yet they still have angular momentum. For example, we have 2 objects that are moving. We want to know what their total angular momentum is about 0.0. So just like with linear momentum, I can find the angular momentum of a system to be the sum of the angular momentums of each particle. We have a perpendicular angle for both of these, so that's nice. So we don't have to worry about the direction. So L1 is going to be M1, R1, V1. L2 is going to be M2, R2, V2. Now we do have to consider direction, even though these are not actually rotating. If you use the cross product R cross P, using the right-hand rule, I put my fingers in the direction of R, rotate my palm towards P, my thumb points into the page for this one. So M2 is actually creating a negative angular momentum. If I do that over here for M1, fingers in the direction of R, palm in the direction of P, that's actually creating an angular momentum that's out of the page, which is going to be a positive angular momentum. So these actually have angular momentums that are partially canceling each other out, even though they're not actually rotating. So I'm going to do M1 is 3.1 kilograms. R1 is 2.8 meters. V1 is 3.6 meters per second. And then I'm going to subtract the M2, R2, V2. So M2 is 6.5 kilograms. R2 is going to be 1.5 meters. And V2 is 2.2 meters per second. So remember that your angular momentum is either going to be into or out of the page, and that is going to depend on whether this answer comes out positive or negative. So in this case, I get a value of 9.79, so I'll call that 9.8 and units of kilogram meter squared per second. It comes out as positive. So my angular momentum, my system, the best way to define this in 3 dimensions would be a positive 9.80 kilogram meter squared per second. in the k-hat direction because it's coming out of the page. Now, angular momentum also relates to torque. So Newton's second law says that our net force is equal to the change in linear momentum over the change in time. So if you have a net force, there is a change in linear momentum caused by an impulse. Well, we have the same idea here with our net torque. So our net torque is equal to change in angular momentum over change in time, assuming that we're keeping a constant axis of rotation. You always have to analyze these from the same axis of rotation. So basically, your net torque causes an angular acceleration. That angular acceleration causes changes in angular velocity over time. So they get this change in angular momentum. Linear momentum is conserved when there's no net external force because you'd have no change in linear momentum over time. Angular momentum is conserved when there's no net external torque. So once again, you have to define a system and determine whether the torques are internal or external. These are two completely different quantities. It is impossible to transform linear momentum into angular momentum. It is impossible to change angular momentum into linear momentum. So it's possible to have situations in which both are conserved, neither are conserved, or one or the other is conserved. You cannot convert one into the other. They are completely different quantities. So here is an example of kind of a conservation of momentum problem where you could have linear or angular. Easier problems are like the ice skate type thing. So if you have an ice skater that is like doing a spin, can't really draw, okay, and they've got their arms out and they're doing a spin. If they bring their arms in, then that's going to reduce their rotational inertia and it's going to cause them to spin faster in order to keep the same angular momentum. That works assuming that the ice is frictionless. And if you watch ice skating, it's pretty awesome to see how fast they can actually get just by pulling their arms in. You can do this yourself with a spinny chair. So if your work chair can spin, get yourself going in the spinning, put your arms out, put your arms in, you'll speed up and slow down. That's conservation of angular momentum. So in this case, we have both the possibility for linear momentum and angular momentum. So this is like the hardest type of situation that you can kind of picture because you have both types possible. So this ball is moving in with a linear momentum. It is going to collide with the rod at a distance away from the axis of rotation here at the hinge. So that ball is going to create a torque that is internal to the system because I'm going to assume that my system is the ball rod system. Now that rod is going to start to rotate. The ball is also going to change its linear motion. So if you think about it, if my system is the ball rod system, this hinge is not a part of my system. And there's really no reasonable way that I can include that hinge because I don't know all the forces on that hinge. You know, is there a wall? I don't know. I can't make my system so big that all of my forces are internal. So this hinge is not a part of my system. When we're defining our system for momentum, whether it's linear or angular, you only want the objects that are physically involved in the collision with each other to be the system. So that's why our system is the ball rod system. So the ball hitting the rod is internal. The rod hitting the ball is internal. The hinge on the rod is external. So linear momentum is not conserved. So whatever linear momentum this ball has at the start is not the same linear momentum that the ball is going to have at the end. Now, the hinge is the axis of rotation. So although that hinge is creating an external force, it's not creating an external torque. So angular momentum is actually conserved. There is going to be angular momentum at the end because this thing is going to be rotating. But where's the angular momentum at the start? Well, the ball itself can be treated just like a point mass moving in a straight line as having both linear momentum and angular momentum. So I am not converting linear momentum into angular momentum because whatever angular momentum I had at the start is the same angular momentum I have to have at the end. But linear momentum will be lost from the system because of that net external force. So when we're looking just at systems with conservation of angular momentum, it's a lot easier to picture. So this is that kind of ice skating idea. So this guy's got some amount of initial rotational inertia with his hands out with these dumbbells in him, okay? And he's spinning with some sort of initial angular velocity. So he has some sort of angular momentum. Now, if we assume that that rotating thing has no friction, then when he brings his arm in, his rotational inertia has decreased, which means his angular velocity has to increase. And that is due to the fact that there's no net external torque. So our angular momentum is constant. So our angular momentum at the start has to equal our angular momentum at the end. So with a lower rotational inertia, we have to have a higher angular velocity. So let's look at an example. So this is one of those kind of trickier examples where you have an object moving linearly and you have a platform that can rotate. So this is a kid that is running. So this kid is going to have a mass and initial velocity. We're going to assume that our mare ground here has a rotational inertia of I and a radius of R, and then it starts off at rest. So I need to figure out, first of all, what I can do. So linear momentum, is it conserved? The answer is going to be no, because whatever is holding this platform in place is going to create that resistive force. So if one of your objects is fixed in place, that linear momentum is not conserved. Okay, we talked about that when we did linear momentum. So linear momentum is not conserved because whatever that hinge is here, that axis of rotation, the axle, is being held in place by external forces, preventing our system from moving freely. Now, that axle is acting at the axis of rotation, the center of that rod, that wheel platform thing. So therefore, we can assume that our angular momentum is conserved. So when I solve a problem, I'm going to state that my angular momentum is conserved. So I'm going to say change in angular momentum is 0. So the angular momentum at the start equals the angular momentum at the end. So I'm going to list out my possible objects. So I'm going to have the angular momentum of the platform at the start plus the angular momentum of the child at the start is equal to the angular momentum of the platform at the end plus the angular momentum of the child at the end. Now the platform starts off at rest. So it has no angular momentum at the start. So how does this child have angular momentum? Well, what we do is we assume that right before the collision, that this kid is located at a radius of R with a speed of V and a mass of M. So its angular momentum would be like I omega. Well, it's a point mass, so mr squared times omega, but omega is V over R, so mr squared V over R. This gives us mrv, which is the same thing as our linear momentum times R, which we had kind of looked at before. So our point mass can be defined as mrv or mvr, whatever you want, or as I omega. Either way, however you define the point mass at the start, is going to be based on m times r times v, because this is a 90-degree angle here. So we're going to have m r times v at the start. Now the angular momentum of the platform at the end is going to be I times omega. And that's going to be I of our platform. Our angular momentum of the kid at the end is going to be I of the kid times omega. Now I'm doing that because they're going to have the same final angular speed because they're going to come together. This is a perfectly inelastic collision. So by the way, kinetic energy is not conserved. So I'm going to actually write that as mrv is equal to I of the platform plus I of the kid times omega. So we have mrv is going to be equal to I of the platform, which I'm just calling I here because they give us that value. I of the kid is going to be mr squared, so that's m r squared. Okay, I'm using this m here times omega. So omega is going to be m rv over I plus mr squared. And we can plug in m of the kid. That does not cancel, by the way. That's 40 kilograms. The kid lands 2 meters from the center. He was initially going at a speed of 4.0 meters per second. The I for the platform is 20 kilogram meter squared. Oh, that's a plus sign. Plus mass of the kid, 40 kilograms, times 2.0 meters squared, which I get an angular speed of 1.78 radians per second. Now it wants angular velocity, so I'm going to assume that that collision is going to cause it to rotate in the counterclockwise direction. So my actual angular velocity, using the right hand rule, is going to be coming up out of the page, so that is going to be in the k hat direction. If it asks for angular speed, I would just have 1.78 radians per second. You could also say out of the page, instead of using the unit vector, you could say out of the page. But if it asks for velocity, it needs both a magnitude and a direction.